Good morning, good afternoon, good evening, depending on where you are. Had a few technical difficulties this morning, so luckily I work in the same office or same building as Dean, so I was able just to join. Thanks to Wood Solutions for, first and foremost, for letting us have a chat about this. We're quite proud of this building. We've been involved now for a few years on it, so it's been fantastic to actually see it nearly complete now. Just go through. So, look, I could talk about this for hours. I've only got 15 minutes, so I'm going to try and touch on the main points that I tend to think we've definitely learned, or items that we've definitely noticed during this design. We were pretty heavily involved in 25 King Street and the design of that, and which is a commercial building, and now doing an apartment building, completely different, completely different experience. So we've really learned a lot along the way. So a few things just to touch on: structural makeup of the building, why timber, why have we actually chosen timber for this particular building, the timber mindset. So that's a bit of a cause, just about really thinking timber from the beginning. How we've kind of schemed it and how we arrived at the final layout of timber. The fire approach, which is always a common question that comes up in timber buildings. Axial shortening, was a really hot topic on this particular building, so I'll just touch on that for a little bit, and then just a little bit on some different kind of connections we've got. That picture you see there is that's actually level 9. So that's actually the last walls, timber CLT walls on this job. So they're installed a couple of weeks ago. So this is a bit of a snapshot of the Revit model, which is a good way to illustrate the makeup of the building. So you can see at the bottom, we've got our traditional kind of concrete base with a couple of levels of basement. We've then got a couple of floors of concrete up to level 1. Level 1 is that transfer floor that we've highlighted there, and then from there up, we've got our timber superstructure that goes all the way to the roof. And we do have a concrete core off the back of the building. It's a bit hard to see there, but it runs all the way up the back side of the building there. And then on top, we've got a bit of a hybrid timber and steel roof structure and a bit of a feature steel pergola as well. One of the things that has come up is in the past is why didn't we do the concrete core out of timber as well? So the concrete core in this instance is the main lateral system for the building. We did a lot of analysis at the start to see if we could do it in timber. The problem with this particular layout of this building, because it's an offset core, it's a long skinny building, there are some pretty high torsion loads in the building, and in the floors in particular, and getting that load into a essentially panelized timber core, the connections between the core elements just became almost totally inefficient, and just really got to a point where you actually couldn't really do it. So Simon will talk a little bit more about what we landed on with that concrete core in his presentation, but from a pure structural point of view, look, it could be done, but it was going to be quite difficult to do. There's a section through the building. This is quite a good section. It's through the long part of the building. You can see the lift core going up the middle of the building and the stairs next to it. Couple of levels of basement at the bottom. You'll notice on the right-hand side that it slopes down. That's because from the ground level, street level, there is quite a rise up from that street level to that particular ground floor. You'll also see just above that rise up on the right-hand side, you'll see some pretty decent concrete beams there. So that's part of our big transfer floor. Those beams there are quite significant as well, because obviously we need fairly open space for the entrance into the building for garbage trucks, that kind of thing. There's also a pool structure at the front of the building there, so that the beams themselves have to kind of work their way around a pool as well, a swimming pool. And you'll notice that the right-hand side, we're able to slope the basement down. Now we actually can't do that on both sides, and I'll touch on that shortly. And then you can have a brief idea of what the roof itself looks like up on the top. So that level is a bit of a combination of a multi-purpose area on the left-hand side of the core, and then on the right-hand side is the penthouse. So why timber? I always find it's when we're doing a timber building, or you're setting out to do a timber building, or it becomes an idea, is really to drill down on why to do it in timber. I mean, Wood Solutions and plenty of other bodies in Australia and internationally, work really hard to promote timber. But especially in Australia, it is still a new product. So that question always comes up of that why timber? That there has to be a driving factor for it to be on timber. So I've listed out just a few of the very many benefits of using timber. Obviously, there's aesthetics reasons. Architecture, it looks amazing. There's the speed of construction. Where a contractor might really see a benefit to speed things up. There's site constraints. When it's a really, really constrained site, you don't have a lot of room, that kind of thing. Sustainability, obviously, ESD is huge benefits from timber. But the main reason for Monterey and the whole driving factor behind Monterey being timber is weight. And then the others above that actually have just flown on from that. So why weight? So this is a bit of a plan view of the site. So you can see the site there, 9 Lambert Street, highlighted. So that grey line that runs through the back side of that building in that plan view is the Clem 7 tunnel in Brisbane. So one of the main tunnels, road tunnels in Brisbane that goes under the river. So that section that you see there, you can see that the basement in the top right-hand corner, and that it is literally over the top of the tunnel. And we have some pretty significant foundations in that area. So one of the main reasons of doing this in timber, and Simon might touch on this a little bit more, but with doing this in a traditional concrete or even steel and concrete building, we're likely to only get around 5 to 6 stories out of it. That just wouldn't be commercially viable for GVG. So by actually doing this in timber and using the benefits of timber being such a lighter structure, we were able to go 10 stories, which actually made the project stack up financially. So really important stuff. And then the way we've actually then made sure that we can actually support this building over the top of the tunnel. So the tunnel has a certain pressure that we can design to at the crest of the tunnel. So you can see there some of the main foundations are all highlighted there with significant loads on it. We're pretty lucky in Aurecon that we've got some really good tunnel engineers who have been involved in the design of that tunnel as well. So that they were able to grab our loads and do some finite element modelling of the soil profile itself, and basically work out what the pressure would be from those foundations on the crest of the tunnel, at the bottom of the tunnel. And we're able to prove that it was within the tunnel limits, and therefore we got the sign off from the authorities of the tunnel. So the timber mindset, so the good news is now we got to a point now that, okay, we now know that it is in timber. So from the outset, we were able to think timber, timber, timber. And that is so important in setting up everything from the start, from your concept and your schematic designs. So what I've highlighted here, these are just a couple of architectural layouts, and this part of it would be really the challenge for the architects who are listening, that when you are thinking timber, you almost have to let timber dictate a little bit as to how you're going to lay out this structure. So what I mean by that is, in an apartment building, often you have different layouts of apartments as you go up the building. And now, obviously, with the timber elements and that, you want to minimise transfers as much as possible. So I worked pretty closely with Jordan from GVG to get to a point where we essentially only had one transfer in the whole building above the main transfer level at level 1. And so you can see there the lower levels, which there's 4 units per level, and you can see there that blue highlighted wall that I've got in there actually drops off on the higher levels. So in essence, we don't actually have any transfer whatsoever. That walls can just help us at the lower levels. But what that means is it makes it really, really quick on site too, because it's just a repetition of the floors. So timber schemes, so just going through where we started. So look, that's a starting point. I've noted a few things there. I won't go through them all, but I mean, generally a few rules of thumb that we work to on this that seem to work as a starting point and to get the most structurally efficient building layout is, 4 to 5.5 metre general spans, up to 8 metres for your beam, your timber beams. Once you start to get, you can go larger than that, but then obviously your floor to floors start to be impacted, especially with services and that kind of thing. And definitely giving yourself enough room for connections. And then also to add to that, the wood solution guides and the supplier design guides like XLam have a really good design guide that are great for these early stages to really scheme things together. Then you look at the final layout, so completely different. And in essence, where we got to with that was actually working with XLam itself and with GVG from the construction side of view to really drill down on what's going to be the best way to do this. And what we ended up with was, yes, we've got slightly bigger panels than what we may have had in that first scheme, but the layout is a lot more simple. So we ended up with all of our panels running north-south, which in terms of the installation, you start at one end and work your way to the other end and you're done. So we could actually fit the whole width of the building in on one panel, which just made speed on site really, really, really quick. The other thing to add to though is wet areas and set downs. So a lot of work went into this, and it's I can talk offline because I could talk for hours for this, but really, really understanding the best way to do the set downs. That's the roof structure. Look, the other thing I'll note about that is the really complex parts that we found on this was definitely in the connections again, and it's often common with timber design, but effectively, combining timber, steel, and concrete and getting connections to work for that, really difficult. So definitely watch out for that. Fire approach, I'm not going to spend too much time on that. We all know about char of fire. What I am going to say is that a big shout out to James O'Neill at Homes Fire, who's been involved in the start of this job. It's really important that we work together with the fire engineer. We had a really good collaboration between us where he would do all his fire modelling, come up with the ideas, and then let us know how we then need to proceed and work together to come up with solutions. So effectively, because it's an apartment, a lot of the walls are going to be covered up anyway, so he can utilise that for his fire protection on this, and that's generally what we've done, other than a few elements which are kind of exposed for aesthetics reasons that we've designed for the char. Axial shortening, this becomes a really, really interesting topic especially when you've got a concrete core. Obviously our timber is going to shrink and swell and it shortens different to concrete. What we did there is essentially we looked at all of the connections of slab to wall throughout the building and really drilled down on just about every level and really looked at what the actual loads are going to be and what's our actual expected moisture change. And then we detailed the connections accordingly to make sure we had a pretty uniform axial shortening throughout the floor. And where we couldn't achieve that with platform framing, you'll see in that picture, we've actually got some little grout blocks there that have effectively strengthened up that connection locally. And we've only had to do them on the lower floors, which has meant the upper floors have still been able to fly through pretty quickly. Connections, look, other than a couple of standard ones that I'm about to talk about, most of the connections were pretty much standardized connections. So we've used Rothoblast in this case. And what I'd recommend there is Rothoblast has some fantastic information and guides and testing information that you can use. Those are the guides there. A lot of it is based on European standards, so you have to be a little bit savvy with European standards, but they're pretty easy to follow, and again, a really good starting point for your actual connection design. So I'll just touch on one or two of the kind of interesting connections that we dealt with. So the half laps, which are pretty standard normally, but you can imagine a lot of them take our floor diaphragm forces, so our lateral forces through the floor. Obviously, our forces as you get closer to the core are a lot higher. So as you can see there, the highlighted in the plan view, what we effectively did there is we reduced the number of screws on those outside elements, and that just meant that it was a lot quicker to install on site. And talking to the actual installers on site, they were pretty pumped in the end that we were able to reduce some of those connections, because you can imagine standing there and drilling screws at 150 centers all day long can get pretty tiring. The other connection, just to have a chat about, I chatted about before about the axial shortening. So when we've got a concrete core and we need to allow for some movement there, so you can see in that picture that's the core on the right-hand side. On the left-hand side is the first timber wall, so that's kind of the lobby space as you walk out of the lift and go into different apartments. And what we effectively did there, and this is all back to the scheming and working out the best, most efficient way, is that we could actually, those floor panels above could actually cantilever past that lobby wall on the left-hand side, which meant we didn't have to rely on that concrete wall for vertical support at all for our timber, which meant we could be a bit tricky with the detail in there and allow ourselves to allow a bit of movement there should the building go up and down a little bit during construction. And I think that's it. That's it for me. Okay. Stop again.
Thank you, Callum. We'll stop sharing our screen here so that we can hand over to John for the next presentation.
Thank you for inviting me to speak today. Again, this has been a project a few years in the making just to get to this point, but it's been a fantastic project to be a part of. So we're really proud to have been a major supplier to the structure. So a little bit about XLam for some of those that might not know us that well, and this is really high level, but essentially our supply chain, we're taking radiata pine from plantation forestry in New South Wales and Victoria. It's going through our sister company's mill, Hind Timber and Tumbarumba, and then it's coming to us where we're pressing it up into cross-laminated timber, manufacturing it into bespoke structures and distributing it throughout Australasia and a little bit further on a couple of projects. But our core market is Australasia. So that's really high level what we're delivering to the market. And just as a general guide, from log to panel on site, we're generally utilising about 38 to 40% of the log, and that's sort of dependent on design, the type of building it's going into, etc. So rather than go through any detail around the manufacturing plant, my sort of view is a picture paints 1,000 words. So this is the XLam cross-laminated plant up in Wodonga. We've been operating for just over 2 years now. So you can see in the foreground our mechanical press, and in the background is all our feedstock preparation for the layups. And then off to the left of that image is all our CNC processing. So again, here's our automation of laying up the panels. So there's a glue line in there. Next layer of panels goes down, glue line, next layer of panels goes down. So this is how we're building up our CLT panels before they go into the press. So single shift in this plant, we're running about 16 people. So it's highly automated manufacturing. Again, this is now over at our CNC line. Again, we're trying to touch the CLT as lightly as possible. So everything we do up to loading packs on trucks, we're trying to do with vacuum lifters, etc., and minimise forklift use, both from a health and safety perspective, but also in terms of wanting to minimise the ability to bruise, dent or scratch any of the CLT going through the line. So just a quick summary metrics on this project. What we looked to supply was just over 1,200 cube of CLT. It worked out to be about 9,385 square metres. It was a mixture of what we call T3 green plus treated and untreated, depending on whether it was being used in wet areas, etc. Total of 1,025 panels of CLT, all up. There was 25 days of manufacturing, or 200 hours, although that was spread over a longer period of time. And we delivered it up to the site in Brisbane in 29 deliveries. The GluLam, there was a further 83.5 cube of GluLam that came from our sister company Hein, out of our Maryborough plant, which was about 1,235 linear metres of GluLam. It was all H3 treated. There was a further 17 days to manufacture, or 136 hours, again spread over a slightly longer period of time. And in the end, deliveries to site, it was delivered over 10 deliveries to site. One of the learnings for us, as we're very accustomed to coordinating CLT out of our plant, but when we're coordinating GluLam out of a third-party plant, we had 2 very large deliveries arrive in Brisbane, and we had to take them back from the site, split them up, and then re-deliver them back to site, in line with how we wanted to sequence the delivery. So, no, it didn't run as smoothly as we would have liked. There was a small hiccup along the way, but we're all learning as we deliver these projects. So, but I wanted to acknowledge that. And we've got that right for some other projects we've delivered as well. So the sustainability summary, and this is really important. I know Callum spoke about what I call the 3 S's. So what are your drivers? Site, speed, sustainability. Sustainability is very, very topical in Australasia at the moment, and mass timber in all its forms has a very big part to play in that story. So for this project, that 1,207 cube of CLT sequestered around 790 tonnes of CO2, and it weighed around 710 tonnes. So if the structure was of equal volume in concrete, it would have emitted about 530 tonnes of CO2, and if the structure was of equal volume in concrete as well, it would have weighed about 2,097 or so. Round figures, say 2,100 tonne. So there was a significant weight reduction, and naturally that was one of the key design drivers for the site, and for the client and the structural engineer was needing that lightweight structure. But that's sort of the magnitude of the difference we're talking about. And then this is a really interesting one. So based on radiata pine plantation forests in Australia, time to regrow all the CLT and GluLam in this project took 1.6 hours. So we've essentially regrown all those trees for the job, within the first couple of hours. So a bit of a focus on procurement. Procurement is varying in forms for mass timber at the moment, and we're seeing a reasonably quick evolution in this space. What we're talking about from a DFMA perspective is, if we're looking at our traditional sort of design and tender model, we do a portion of design up front. We get the building to a level which we can get a constructor can get a number on it. And then essentially we're handing over to a main contractor, who then takes the time to deliver a building. So what are we looking at in terms of off-site manufacture? We're looking to reduce on-site labour costs. We're looking to speed up the construction, so we're looking for a reduction in financial holding costs. We're looking for reduction in site risk, in terms of the longer you're on site, the greater level of risk. And I'm talking about risk from a perspective of weather off days, etc. and also material risk. So typically, what we're doing is we're spending more time in the design phase and more time in the construction sequencing phase, so that we can speed up that construction phase. Pre-construction, so what becomes really critical in this space is our pre-construction dates. So we've got a production slot which we need to stick to, and this is really important in terms of understanding how DFMA in all its forms, not just mass timber, actually influences the design process. So we've got to create some space for this manufacture duration, and how we kick that off is we're needing those frozen architecturals and structurals. So this is, diagrammatically, high level what we're looking at. So for off-site manufacture or DFMA design, we need a slightly longer and more detailed design process. We need to create that space for manufacture, and then of course we can truncate that construction period. And for overall project, we look for a reduction in procurement of a building from design through to practical completion. So where are we typically looking to incorporate DFMA? So whether it be design for manufacture and assembly and mass timber or any other form of design for manufacture and assembly, we really need to be kicking off at that prelim design stage, which again is what Callum spoke about. So the key here, especially with mass timber, which is an emerging technology, an emerging construction methodology, what we're finding is a lot of clients are coming to manufacturers like ourselves, but others in this space as well, with some 60% DD drawings and saying, would this be suitable for timber? Sometimes the buildings are absolutely suitable for timber, but the challenge is we've already designed 60% of the build. We've already theoretically burnt 60% of the consulting fee, and so to wind that design back to then be able to proceed with a mass timber building is more and more difficult. So we need to start at the very beginning. So again, what we can provide is preliminary price guides, typically around that DA approval of an architectural pack, and we can get a rough number for what the building is going to look like. And Kangaroo Point went through this exact process, albeit we actually went through this preliminary price process 2 or 3 times, but we got there in the end. So then, in terms of the procurement pathway beyond that detailed design or that DA approval and into DA design, developed design, what we're looking for is the appropriate level of detail for the appropriate style of procurement. So what we're typically seeing in the market now is if we're in a tender environment or a negotiated contract environment, we're really needing a level of design which is commensurate with sort of certification design. So we need a really good set of construction architecturals and structurals to be able to give that hard number type approach to procurement. The other thing we're seeing is we're seeing a lot more ECI work in the mass timber building space, which is great. This is typically kicking in around that developed design period. And at that stage, we've got enough information which we can move forward with approaches around, a must not exceed gross maximum price, et cetera, et cetera. So the other thing you're quite often seeing with an ECI type approach from a design perspective is you're seeing the structural engineer has got the design to a position where we roughly know how the building's going to go together. We may not have all the connections fully detailed, and you'll see a lot of notation coming through, such as connection to be determined by manufacturer. So, you know, the design's almost there, but that final piece, which is the devil in the detail, is really being driven by the particular manufacturer that is going to supply that job. And there are idiosyncrasies within mass timber manufacturers, whether it be CLT, XLam, or LVL. So this is quite a useful process to go through in terms of that ECI, pick your partners, and then move forward. So again, the commercials, one of the things which we're seeing a lot more of is if we're in an ECI environment or a tender environment, we need to be negotiating the commercials in parallel to the price. So what we're finding is when we try and do these things in a linear fashion, what we're doing, because there's still a start date for being on site, we're actually starting to truncate that shop drawing process and that manufacturing process, because your start date very seldom slides. And so, you know, we're creating pressure on the project, which if we're actually running the commercial review in parallel to the price review, we can try and keep some of that pressure off the period you need for shop drawings, manufacture, and logistics to site. And then contract to site. This is very rough, but it's typical for most builds in Australasia. Lead times, we're looking at 12 weeks plus or minus a couple, and that's really depending on scale and complexity of the project. We naturally, you know, if you're building really significant towers, etc., you know, that lead time is going to differ a little bit. But this lead time generally is commencing from frozen architecturals and structurals, so that we can actually kick off the shop drawing process. And then roughly how that 12 weeks is broken down, we're looking at about half of that being the shop drawing approval process. And then the manufacture duration is about, it can be anywhere between sort of 20 and 30%, depending on again, the size and complexity of the project. And then into logistics of actually getting panels to site, there's typically only 20% of that duration. That's to the kickoff, and then naturally, you know, we're delivering 29 trucks over a construction program. So diagrammatically, the other thing that we really want to sort of see a lot more of when we're engaging design for manufacture and assembly, and particularly in mass timber, is when do we get all the different consultants in play. So a common sort of team and design approach, you know, we've got a prelim design team, obviously we've got a client, an architect, planner, cost consultant, probably a client's project manager, and then we're into around that DA, DD period. You know, we're now starting to expand the team, and there's a structural engineer, an acoustic engineer, and fire and mechanical, etc., all coming to town. And then we're out to market, talking to builders and main contractors and the like. So that's sort of how we traditionally see projects coming through the pipeline, which is relatively straightforward. What we're looking at in terms of needing to tweak the process a touch for design for manufacture and assembly, not just in mass timber, but DFMA in general, is we're needing to see a slightly different level of engagement of that consulting team. So structural engineer right up front beside the architect, making decisions about what that primary structure is going to look like. And I think this project is a really good example of where that occurred. Now we're into that sort of grey area of DA, DD, somewhere in there. You know, if we've got a builder main contractor in play, then it's either a design build like Kangaroo Point, or we're into an ECI type involvement. But of course, the other additional piece is actually starting to not so much choose who you're going to manufacture this with, because we still need to maintain some commercial tension, but at least limit the palette of off-site manufacturers. So is this going to be international, is a project going to be internationally procured, or is it going to be domestically procured, or is it going to be a mixture of both? Because that actually has impacts and design constraints that need to be taken into account by the architect, but in particular by the structural engineer, fire engineer, mechanical and structural and acoustic. So that's really important. And then we're into that traditional space of, we're all here delivering a building. But what we're needing to see is earlier engagement of some structural engineering and either early engagement of your off-site manufacturers and or at least making a conscious decision during that design phase around how that building's going to be procured. And we're doing a lot more of this these days. So the next piece, which links back to, again, what Callum was talking about and what I've referenced earlier, when do we actually need to be thinking about DFMA, i.e. is this going to be a concrete structure? Is this going to be a steel structure? Is this going to be a timber structure? Do I just want to build a traditional building on site, or do I want to engage off-site manufacturing? I know this sounds simple, but that has to occur at prelim stage. Optioneering between the three main structural elements, when you're down at DD or certification, it just doesn't help anybody or the project. So first principles, we need to be making some conscious decisions around materiality, DFMA, etc. And that comes back to the classic around fundamentals such as grid. So again, 4.5 to 5 metre spans for mass timber, for domestic or apartment living applications, great. If it's a commercial space, you're looking more at, somewhere between 6 and 8, but that classic 9.5 grid is actually quite hard to achieve in timber. So we need to be making these decisions really early on.
Excuse me, John, we're starting to be late on time.
Sorry?
We're just running a bit late on time, so if you can keep
No worries, that's cool. When do we need to be actually engaging those off-site manufacturers? It's around that DD stage. So final piece, and this is just 3 or 4 images, and then I'm done. What does that shop drawing process look like from a DFMA, sort of an off-site manufacturer? What we're talking about here is not just a set of shop drawings. We're talking about the full BOQ for the job, or all the CLT, GLT, fixings and bracketry. We're talking about manufacturing drawings, assembly drawings, loading docs. So this is what you see back. So we're essentially completely redesigning the building, ready to be able to go through a CNC machine. We're then actually sequencing the construction, which becomes a bit of a Bible on site as to how we're actually going to put this thing together. The replication of all those connection details that Callum and the team delivered. And then we're actually sequencing every single truck, where every single panel is, so that when we get to site, we know what the first panel on is, we know what the last panel off is, we know where they need to go in the building, we know their exact weight. So this is some of the stuff that comes with off-site manufacturing. That's it. Thank you very much.
Thank you, John. So yeah, if you can just stop sharing your screen, and now we'll hand over to Simon.
Thanks, guys. I have skipped my presentation and just running a video while I talk, so you can hopefully learn a bit by what you see in addition to what I say. The guys have covered it pretty well, so exactly what Callum and John have explained is basically what I'm going to tell you how we put it into practice on site. Apologise at the outset, I am sporting a bit of a cold, so being in Queensland, I'm sure it's not the dreaded sea. As far as methodology and the design aspects that led into our construction, as Callum mentioned, we had a concrete core, which we achieved by using a permanent formwork system. And
share your screen.
You can't see my screen?
Not at the moment, no.
Sorry.
That's great.
Yep. Great. I won't rewind it. You've just missed seeing a truck unload. And I'll keep going with where I was. Sorry. So the permanent formwork system, we had intended to try and get that done in the 5-day cycle that we thought we could achieve with the timber, which didn't quite work out to be the case. And as far as time goes, we were very much impacted by the concrete core taking about 7 of our 8-day cycle. And if we were theoretically able to construct this efficiently with a timber core, so all of the elements, wall and floor being timber, we would have saved about 35 working days on site. Most of the CLT that we installed was fire protected by direct fire rated plasterboard. We did, however, keep the soffits of the balconies and the hallways exposed just to try and get the body of the element of the structural element of the building shown, so we could tell that story. Key consideration, as was mentioned by Callum, but also with all of the other consultants, was working in the ceiling heights and the ability really to bring that forward. And one of the big outcomes of working with CLT is it forces you, because of the offsite manufacturing aspects, and really you've basically got one shot at getting it right, forces you to use the technology that we've got in BIM and whatnot to try and bring more control back to the designer as to how things are going to work spatially, and leaving a lot less up to the workers on site, which has been quite a benefit as we've come to install things now that we're fitting out and putting all the services through. The ceiling heights that Jordan and Callum and the other service consultant team worked out are actually playing out, and the guys on site are rolling through pretty quickly on the internals. In terms of the solutions that we had to come up with, there's a lot of work that goes in from design and consultant, and as both Callum and John have mentioned, the early contractor involvement is a key thing you hear again and again when talking about CLT. Excuse me, the solutions that we had to try and come up with to deal with fire and water and other aspects of the construction that CLT differs from other methodologies actually gave us the opportunity to deal with other problems. So every solution that we looked towards, we tried to get another benefit out of. One of the key things with our developments with the higher end market in Brisbane is that there's an expectation that we will have set downs, for instance, in wet areas, so that we have no transitions. We have to step up into wet areas. We looked at various options there to try and achieve that, and we ended up settling on actually building up the areas outside of the wet areas with an aerated concrete. And when we did the cost benefit on all of the different options, using timber, using wet pour concrete, the aerated concrete gave us a really good outcome to solve an acoustic problem. So that was really the story with a lot of the solutions that we came up with on site. In terms of the process that you're looking at now, the CLT process itself, because it was probably the main focus, as the Meccano set, or the IKEA set that you think of when the focus is putting the timber together. As you can see, there's 2 guys predominantly with a crane crew putting this whole thing together. Tyson from XLam really led us in helping us, and Savcon down in Sydney helped to establish our process. And by level 3, which was our second level of CLT, we basically, the whole thing was working like clockwork. We had a really gun guy working out all the logistics and planning with all the off-site deliveries and crane lifts, and the on-site crew, as you see, with a very limited number of hands on the deck, installing the thing. So the lifting order is worked out by Tyson and his team down at XLam in Melbourne is crucial, and they consider that all in the shop drawing, which I think is one of the major benefits of working with a local supplier such as XLam, to work the order so it comes off the truck in the order and the right way up. When we did have to flip panels, that is when the whole pit crew process really falls apart. And XLam guided us in that area, and when we, by our own needs, had to flip panels, we saw how much of a drama it would have been had that not been the case. One thing that we didn't probably anticipate in going into this is the amount of space that we'd require on site. We were sort of wrongly thinking that we would be installing these panels off the back of a truck, much as the same way as we would in a precast situation, where a precast truck would turn up and you lift panel by panel as the truck sits down on the ground and lift them into place. As you saw, the shop drawings that were sent there, and some other pictures you might have seen, the trucks roll up and we basically unload all of the CLT onto a space on site in about an hour, and then from there we lift them up onto the live deck. That did require us to create some space, and because this building was on a long, narrow site and we're built pretty well out to the boundary in all faces, that required us to build some elevated platforms to locate those. And we were lucky we had some friendly neighbours that were very generous with their backyards. I would suggest for those builders out there and other people considering what you can use to most efficiently unload and load up the panels, you'd probably need to have two spaces around 15 metres by about 7 metres wide to be able to land that the timber, just so you can sort it and have it brought up in the right sequence. And as you can see with these panels here, we're not loading up the deck; they're very clear and open, which allows for efficiencies on site. Specific learnings on site from the CLT construction, things that we didn't know as we went into it. The dew point analysis, we had worked with some people down at the University of Sydney at the recommendation of Rutherglen, and one thing we didn't consider with that when we went into the project was that we'd be actually putting the insulation on the outside to keep the building warm and to avoid having any dew points within the building envelope and affecting the timber in terms of decay and deterioration. The temporary works with timber, obviously trying to keep the floor to floors down. There was less load that we could load up than we would have in a concrete floor situation, so we had to be more get some temporary works plans and loading diagrams done, so when all of the loads of internal finishes and plasterboard and whatnot, we could only load up certain amounts of weight on areas of the project as we went. Scaffolding attachments, so fixing the ties to the outside of the building to support the scaffold, supporting the loading bays and the hoist and crane connections, just all need a little bit more thought, because just about everything we come across, people haven't dealt with it before, and if they have, they hold the IP pretty close to their hearts, and we had to sort of do a lot of digging and working, and the earlier we got involved with that, the better the outcome. And in the same vein, educating the subbies. So a lot of subbies we thought would be really excited to work with the timber, but we did find that a lot of them sort of tried to build factors of safety into their pricing, and we really had to engage with them early and convince them that, look, this is going to be a lot easier, a lot quicker, and you're not going to have to get your hammer drill out and pre-drill all your holes to fix things into concrete. And now that they're on site and working with it, they're really finding the benefits, not only with time, but workplace health and safety, with the issues surrounding silica dust on construction sites. When you're working with timber, you're not dealing with any of those issues. Just wary of time. I'll wrap up pretty quickly. And speaking of time, we did aim for a 5-day floor cycle with the concrete core, which was the driver for that. That floor cycle was consistently 8 days. Once we got to level 3, we set our completion date for landing our last panel on the 26th of June, and we did achieve that. The other considerations, as John had mentioned with his procurement timeframes there, you've just got to have your architectural drawings locked in and get the shop detailing done about 10 weeks out, and just make sure that we've got about a 10-day time frame to confirm deliveries from down south. With the program, we did take a bit of a conservative approach. There is the ability to be able to keep up with the internals pretty closely behind that 5-day slab to slab turnaround, but we were just not wanting to run into any problems and kept a 2-floor buffer so that if we did have any issues with water, that we wouldn't find the internal linings being affected. Cost-wise, always a key question. It's quite a subjective one as to what to compare it with. I see some people on the questions on the question feed there have been asking the same thing. I would say in the residential space at the moment that there is an increased cost over a traditional block and concrete type of construction, but there's other drivers there that make this thing stack up, and more we're dealing with sites that we need to build over infrastructure like we have here, or over poor ground, or over the top of other buildings, and being able to maximise the yield on those sites is what's driving that. In terms of wrapping up, key considerations from our learnings here is the early contract involvement, and the more you can bring forward, the better. You do need to be prepared to do a fair bit of work in terms of finding solutions. The IP of those who have been in the space, they do hold that pretty close, but with a bit of effort, there is the answers to be found. And XLam, tying in with someone like Aurecon and certainly Wood Solutions, are a great source of knowledge, and work well to try and put us in touch with the right people to get the answers. Be really good friends with your fire engineer. He was pretty much a hotline for a couple of months there, but we solved everything in that space. And make sure you do just consider the landing space on site, with being able to get timber off the truck and up to the floor. So thanks for listening. I'll sign off there.
Okay, thank you, Simon. Can you just unshare your screen? I'll just bring my screen back up. And we've got time for just a couple of questions. We are nearly at the time limit now. So I'll just bring up my screen again. Share. So can each of the presenters just go in and maybe one each just have a look at the questions? So you have a chance to...
I'll go first. I'll go to the top. I'll start at the top. So Felix, what are the load and stress levels relative to the ultimate load bearing capacity and utilisation levels? Look, it varies throughout the... We had numerous walls throughout the floor, all with different loads on them, all with different beams landing on them, all that type of stuff. So it's a bit hard to kind of generalise that. So it did vary throughout there. I'd say again, like XLam, their design guide on that has some really good information on what you can and can't really get away with, and they have all their stress characteristics of their timber, so it's a really good spot to go for. I'll just go through. Is there a template for the angle of the screws? That was for Simon. I think Simon will probably answer that. But yeah, generally.
Yes, there is. Rotherblast have a range of templates, yep, and jigs.
I'll just go. Who did the engineering design and certification? Was it done by Aurecon or done as DNC? So Aurecon have done this particular one. Regarding the fire strategies, the fire resistance achieved through a combination of plasterboard and charring. Essentially, yes. In some cases, didn't even have to worry about charring due to the fire check that's there. So what I just recommend there is that really comes down to your fire engineer and early kind of communication with your fire engineer. I've just gone skimming through some of them here. What CLT wall and floor thicknesses do you use? Again, they varied. Most of the floors are around the 200 thick. Some slightly smaller, some slightly larger, depending on the span. And then the walls vary a bit as well. Generally, some of them are around 200 thick as well, but some do go down to, on the upper levels, do go down to the 130 or 125 panels because there's obviously less load. And then I don't know if Simon or John, you guys want to have a bit of a skim through?
I'll answer a couple of the ones there that look like us. Heavy wet weather, we were lucky. We didn't have too much until recently, wet weather, and then it wasn't Brisbane monsoon. We kept a buffer of 2 floors between where we were sheeting internally, and then we had a range of strategies. You might have seen the tape that tapes up the joins, and then we rolled out sheets of plastic, effectively tarpaulins, to try and to protect, and had squeegees on site to get the labourers to go and push the stuff off. So it wasn't too much of a factor. We think we dealt with it pretty well, but we weren't really tested in that regard. And there was a question there about QFES. We tried to work with XLam about 5 years ago to try and get a project in Windsor underway, and we found that we got tripped up at the QFES level. It was just going to be too hard. We found completely the opposite this time round. We did pair up with Holmes Fire, who were excellent in terms of their knowledge of timber, their attitude towards using timber, and their relationship with QFES. And QFES were really only interested because it was in the news at the time about the cladding side of things. So yeah, QFES were really proactive.
Thanks, Simon. Maybe John, if you can answer 1 or 2 questions. I know, Simon, you have another meeting to go to, and some other people probably do as well. So we'll just have maybe a couple more questions, and then we'll wind up.
A couple of questions around the sustainability stuff. So the sequestration of carbon is developed off EPD, so it does take into account machinery for processing feedstock, and then our own processing, and of course freight to site. So you generally get a calculation at factory gate, and then you can add on whatever the relevant distance is to site, but it's usually within margin of error. And then plantation forestry, that calculation is actually based on all plantation radiata pine in Australia, and the growth rates and planting rates, etc. So that's a calculation which we get given. I couldn't tell you the area that's based on, but that's what that calculation is based on.
Thank you, John. We will have to wind up there. If anybody does have any further questions, please feel free to get in touch with the Midrise advisory team, and we can pass on your questions or see if we can answer themselves. Just a reminder, next week we have the Mia Storna project, the 18-storey timber project in Norway that we're going to be hearing about. And please join with me in thanking our speakers virtually. We can't give a big round of applause, but it's been really good having everybody join us today, and we look forward to joining you again in the near future. Thank you.
Thanks, Dean. Thanks, guys.